Okay, now let's look at doing some work with complex numbers. Now, complex numbers, a lot of people struggle with them because they represent values. In this case, it could be imaginary, like the square root of -1. It doesn't have a true value, and it makes it hard for us to picture what that actually represents. Complex numbers can be graphed on what's called the complex plane, where what would be the x-axis is called the real axis, and the vertical axis, which for us normally is the y-axis, is the imaginary axis. So if I had a complex number that was a plus bi, I would go over to a on the real axis and up to whatever b is on the y-axis, and that would be the location of that point on the complex plane. Now, complex numbers, in terms of their usefulness, what they provide us are ways that can make equations equal 0 that are not necessarily x-intercepts or real numbers. So basically, they're just ways that we can take equations, make them equal to 0, find all of their roots according to the fundamental theorem of algebra, even though they may not necessarily be real. So to start with, let's just look at a graph on the complex plane. Let's identify what is this complex number here. So basically, think of it in terms of coordinates. That coordinate has an x value of -1 and a y value of 4. So -4. So if this was on the xy plane, it would be -1, -4. However, this is not the xy plane. It's on the real and imaginary set of axes. So I have the real part and the imaginary part. And our complex number, which would be written as z equals a plus bi, I just put in for a and b. So a is -1, that's my real component. B is -4. So this complex number is -1 minus 4i. Now let's say I had multiple numbers together and I wanted to simplify an expression involving complex numbers. The process is no different than just combining like terms. All I would do is fully expand, put the real parts together, and put the imaginary parts together to end up with a single one complex number. And the same rule applies if we're timesing complex numbers. Basically, you're going to distribute and then combine like terms from there. There is one little hiccup, and we'll get to that in a minute. So I'm going to go ahead. I'm going to do the multiplication. I'm going to multiply this problem out. And the part that's different is when you multiply the I components together and you end up with this number, in this case, -24i squared. Remember that I squared is equal to -1. I squared is equal to -1. And when I do that, I need to substitute that in for the I squareds. So it'd be -24 times -1, and then proceed to combine my like terms. Same rule applies if we're squaring complex numbers. Treat them like binomials. So you could write this as the product of the two complex numbers, -2 minus 3i times itself, or you could apply our algorithm to expand to square. Either way, it all makes the same. So I FOIL this thing out. We end up with 4 plus 12i plus 9i squared. And remember that I squared makes -1. And then combine your like terms from there. And we get -5 plus 12i. Now let's go to division of complex numbers. So you figure out, well, how in the world do I divide complex numbers? We go through the process of rationalizing. What we're going to do is we're going to multiply by the conjugates of the denominator. The conjugate is nothing more than finding this complex part, or if irrational part, but we don't have the square root in this problem. And you're going to change the sign. So the conjugate of negative 2i is positive 2i. So I'm going to multiply the bottom and the top by 2i. And I'm going to rewrite. So when I do that, multiply my fractions together, I have 2i minus 6i squared over negative 4i squared. And what that gives us, we'd have 2i minus 6 times negative 1 over negative 4 times negative 1, which is 2i plus 6 over 4. So I removed the I out of the denominator. Now to write it as a complex number, we're going to split these two fractions. So 2i over 4 plus 6 over 4. And then I'm just going to simplify it and write it with the real number in front. So I'd have 3/2 plus 1/2 I. And let's do one more division problem. This time, instead of a monomial complex number, we have a binomial complex number, and I want to simplify that division. So we're going to multiply by the conjugate again. This time the conjugate would be 1 minus 3i that we're going to times to both the bottom and the top. And then we're going to multiply this together. So my numerator is going to become 3 minus 9i minus 2i plus 6i squared. My denominator, difference of squares here, is going to be 1 minus 9i squared. And the reason why I multiply by this conjugate is because it removes the imaginary or the irrational part. In this case, so it's going to remove the imaginary part of the denominator. And combine our like terms, we'd have 3 minus 11i, and then plus 6i squared, which is negative 1, over 1 minus 9 times negative 1. That's going to give us negative 3 minus 11i over 10. And we just split that. So it looks like our complex number form. So negative 3 over 10 is the real part, minus 11 over 10 times I. And last operation we can encounter would be the absolute value. And the easiest way to talk about how to do the absolute value of a complex number is to start by putting that complex number on a graph. So if I just make a real rough graph here, so the XY plane, now that's going to be in quadrant 3, and the reason why I know that is because I have the real and imaginary axis. And so the real part of that is at negative 2, the imaginary part of that is at negative 4. So this number is somewhere right around in here. Now, the absolute value, what the absolute value represents is the distance a number is from 0. So basically, I want to know exactly how far away is it from the origin on the graph. Well, to get that, we can make a little triangle here. And we have a right triangle, and the horizontal component is 2, and the vertical part of this is 4. And basically, the absolute value is going to be the hypotenuse of that triangle. So c squared is going to equal 2 squared plus 4 squared. So c squared is going to equal 20. Take the square root of both sides and simplify. So c would equal the square root of 20, which is equal to 2 roots of 5. 2 roots of 5 is what the absolute value of that complex number is.